Hello, my name is Ertuğrul Sönmez. I'm glad to see you here in this session with the topic a 2-channel 100 watt stereo full bridge gallium nitride field effect transistor high fidelity class D audio amplifier. Okay, this bulky topic has been performed by our students in the project as a part of our LEM master program at Reutlingen University. So the Reutlingen University is at Reutlingen, yeah, and our center in which these topics have been performed is called Electronics and Drives, which is in the vicinity of Reutlingen. Formerly, our center has been called Robot Bosch Center. So, in the next slide, I would like to present you shortly our agenda. The agenda consists of the content of our master's program, Power and Microelectronics, Leistungs- und Mikroelektronik Masterprogramm auf Deutsch, and the students' project itself, which is a part of this program. I would like to concentrate on to present you our master program Power and Microelectronics, LEM. So all we do is centered around the students project, which is here in light blue. So the light blue blocks are the core, the aim of our master's program. So the supporting processes and key success factors are on the lower side, also light blue, our design environment, our support team, the lab, and the foundry process, which enables these students' projects. But these topics are all given in more detail by my students later. I would like to give you more details about the master's program itself, and this is the dark blue block. These are the dark blue boxes. And at the left side, you see the IC design, the IC layout, and the basics. At the right side, you see the power, semiconductors, and PCB design. Let's start with the IC design. The IC design itself, there you will learn what to know about to be able to design an integrated circuit. Starting from the basic circuit structures, going to basic sources, and then going towards systems like low dropout regulators or switched capacitors, AD converters. So the circuits are not by themselves functional, so you have to transfer it into an appropriate layout, which is called the IC layout. And how to do that is taught in the block IC layout to get an appropriate GDS2 file, taking into account the technologies which is underlying. To be able to follow up all these procedures, you have to know about feedback control theory and also mathematics. So all this stuff is at the left-hand side. So in the master's program, you have also read about power electronics. So the power electronics is at the right-hand side. In the lectures for power electronics, you learn about all the topologies which are now modern applications, DC-DC, AC-DC, DC-AC converters, and their properties and their choosing aspects which is used in which environment. And for what we use in our center, the power electronics, predominantly for electrical drives. So you also learn about the electrical machines, how to control them, and which circuit topologies are used to do that. No power electronics does work without semiconductors, power semiconductors. So you learn about the semiconductors, the carrier transport mechanisms to build up a silicon, gallium nitride, and silicon carbide semiconductor. And the last step in this process is after you have your design, you have to transfer it also into a board, a printed circuit board. And these designs for the printed circuit board does only work if you take several topics into account, like electrical, thermal, and radio frequency aspects. After knowing these topics, you are able to do this student project. And this will be now presented by my students. See you later.
Hi everyone. I'm going to describe the specifications for the system we had to develop in our one-year student project on this slide. The task was to develop a stereo audio amplifier with an output power of 100 watts per channel. In order to identify the project and present it on social media, it was mandatory to find a project name. We agreed on the name Shell, which is an acronym for Stereo Hemmed Electric Loop Amplifier. Here, the system we've developed and set up is shown in advance to illustrate the required specifications. At the input of the amplifier, it should be possible to connect stereo signal sources as well as mono signal sources, for example, an electric guitar or a keyboard. The signal is modulated by a delta sigma converter to a pulse width modulated signal. The modulator has to be designed as an integrated component, which is depicted in the central left of the picture. In addition, the integrated component shall include an adjustable loop delay for keeping switching frequencies lower than 1 MHz and also an adjustable dead time. The now generated signal shall be amplified by a power stage using gallium nitride transistors. In our specific case, we chose Silicon Labs half-bridge gate drivers and EPC GaN transistors. Furthermore, the power stage should ideally work without additional heatsinks. A suitable filter structure is to be selected in order to filter the amplified signal for audible range. All mentioned conditions should be fulfilled with the addition to realize the amplifier size as small as possible.
Hello everyone. On this slide you see a list of all members which were involved in our project. On the left side you see our small team consisting of 6 master students, each with a different role to better split and organize our tasks. In addition to the technical details, each of us had little, if any, previous exposure to the theory and practice of ASIC design. This is why the support of 3 ongoing PhD students and also 2 professors were needed. We had weekly sprint meetings where we defined small working packages and milestones for the outstanding tasks. I would want to point out that it was especially challenging making such a complex project feasible during the lectures and also lab assignments. And here on page 2, I showed you a little timeline of our project. And in the first half of the project, we defined the system's architecture and set up top-level simulations to verify the basic delta sigma modulation principle. After verification, we designed our ASIC using Cadence tools and commercial semiconductor fabrication processes provided by the X-Fab in Germany. Particularly exhausting to comply was the tape-out deadline, which was dated right after our exams and extended our term. In the second half, while the chip was fabricated, we designed and manufactured application boards. It took us several iterations to complete our final board. Several passive filter components were analyzed and compared. Layouts and the fast switching operation of the GaN drivers and GaN FETs were measured and optimized. In the end, everything went fine, and our system prototype was brought to life just before the end of the term.
Hi everyone, next up is the ASIC design and the requirements to realize the ASIC in only 5 months from circuit design to tape-out. At first, I would like to say something about the boundary conditions to realize such a project. When we started in March to develop our circuit design, we all had only one lecture in integrated circuit design. At the beginning of the project, PhD students gave us a cadence training and also technical support during the entire duration. Before we started layouting, PhD students set up a complete development environment in Cadence Virtuoso. Without the support of the university's teams, it wouldn't have been possible to implement a project in such a scale in short time. As a conclusion of our work in Cadence Virtuoso, we simulated and designed an ASIC with provided IP libraries, especially A cells and D cells, which are pre-built libraries that were provided by the chosen wafer manufacturer. One of the biggest challenges were the requirements of the manufacturing process. A high reliability is needed to realize a project like this in 1 year, since there's a deadline of 2 terms for finishing the student's project. It is also mandatory to have a reliable supplier with long-term planning capability. To keep the costs low, it is of a great advantage that wafer manufacturers provided multi-project wafer runs. X-Fab in Dresden, Germany meets all these requirements that we were able to finish desired goals in time.
Hello everyone. Next up is PCB design. With high power Class D audio amplifiers, layout is often critical for achieving maximum power and optimal performance. Though the relevant frequency range of an audio system is 20 Hz to 20 kHz, we still have to consider high frequency design rules when designing the PCB. For example, the ground plane. Because of the fast switching speed and high current flow of the GaN power stage, referencing the input, modulator, driver and filter grounds directly to the ground plane can cause issues. So instead of using a solid ground plane, a proper star ground connection scheme is recommended. An important task of the project was to design and implement the circuit and fast switching GaN devices in a way that no heatsinks are necessary. So naturally, thermal design and optimization was another critical part of the PCB design. Part of the project was also to develop a compact and modular design as basis for future projects. Studying different modulators, GaN devices and filter designs is a current research focus at Electronics and Drives. So, what has to be considered when working with GaN? In order to reduce parasitic inductance, attention should be paid to minimize the physical size of the gate loop, seen in the left picture in red, and also the high frequency power loop, seen in yellow. Doing so enables optimal performance of the GaN device when in fast switching high current applications. Soldering GaN was also not easy at first. As seen in picture on the right, it's obviously difficult to perfectly position a device with such a small pad size and pitch. Additionally, a clean and vibration-free work environment, as well as the correct temperature profile, are paramount to reliably attach the GaN die. Now, for the final part of our presentation, we would like to give you an insight in how we worked during our one-year project. There will be a short video shown in the window where you can see me right now. Therefore, we'd like to ask you to enlarge the speaker window so that you can follow the video. We thank you for your attention, and if you have any questions, we will be available in the Q&A session after the video.
Hello, my name is Manuel Kaufmann. I'm a member of the Shell team at Reutlingen University, more precisely at Electronics and Drives, a research center at Reutlingen University. We are here at the students' workroom where my fellow students and I were working on a project. We would now like to explain our project in more detail in the next steps and show you the individual components of our Class D audio amplifier. Our Shell Class D audio amplifier is shown on the whiteboard. The amplifier consists of 2 channels, but here only one channel is shown symbolically since both channels are systematically constructed in the same way. The audio amplifier is a delta sigma modulator consisting of 2 parts, an integrated part and a power stage. The integrated part consists of an integrator, a comparator, a loop delay, and a dead time, both developed by ourselves. The 2 blocks are adjustable in their time. At the end of the dead time, there are 4 signals which are then fed into the power stage. 2 gate drivers control 2 GaN half bridges, which then amplify the modulated signal, which is then applied to a loudspeaker. The signal is formally filtered by a low-pass filter. The amplified signal is fed back via a feedback structure to the integrated signal processing to be able to correct errors.
Hello, my name is Sascha Eidenschink, and I will show you how we realize the just described ASIC in Cadence Virtuoso. As you can see, the chip consists of two parts, the SD structure and the signal processing. When we dive deeper into the signal processing block, we can see that it consists of the two channels of our amplifier and test structures to characterize and test individual components. If we then dive even deeper into the lower levels of the schematic, we can see the individual building blocks of the two channels and will eventually arrive at the pre-designed cells of the XFAB.
Hello, my name is Marcel Kleinkonrad and I was responsible for the simulation. For verification of our system, we used Cadence ADE-XL for the simulation. We used sinusoidal voltage sources with different frequencies and amplitude as input signals for our system. Here, for example, we used the input frequency of 1 kHz with an amplitude of 1 volt full scale. This signal gets compared with the violet feedback signal from our power stage. The difference between those two signals generates the desired pulse width sequence. As we sweep through the sequence, the modulations process becomes apparent. With closely spaced pulses, we get higher output voltages, and vice versa with the wider spaced ones, as you can see here on the left side. Looking at the DFT, we see switching frequencies of around 1 megahertz, which is here on the right side, down to 250 kilohertz, which are highly attenuated by our low-pass filter. It's around 70 to 90 dBs. And in our audio baseband, which is up to 20 kilohertz, we see the desired input frequency of 1 kilohertz.
Hello, my name is Fabian Hermann and I would like to introduce the layout of our ASIC. As already mentioned by Sascha Eidenschink, we see here on the left screen the schematic of our ASIC. And here on the right screen the layout. As you can see, we have placed our ESD pads in a circle on the outside of our ASIC. In the upper part of the ASIC, we put the useful signals on the ASIC, in the lower part, the test signals. On closer inspection, our two channels can be seen in the upper part of the ASIC. Here you can see the first channel, which is connected to the second channel by a bandgap. In the lower part of our ASIC, you can still see all structures in really built as test structures. We have implemented this so that we can test each structure for its functionality.
After 6 months, our processed ASICs arrived. The chip's dimensions are 2 by 3 mm and the pads are bonded in a 44 CLCC pin package. In the meantime, we spent developing, layouting and manufacturing our PCB. Because of the fast switching speed of the amplifier and the constraint to not use any heatsink, the electric circuit design was especially challenging. Developing a functioning board involved a lot of trial and error. An especially big challenge was to solder the GAN device, which was 75 pads and the bottom side with a pitch of 200 micrometers. After the schematic was finished, we started with the manufacturing process, which is shown by the time-lapse in the background. For our first PCB, it took us over a week to figure out how the process parameters are optimized. After 1 year of hard work, we finally were able to test the whole system. The ASIC was attached to the PCB and several measurements were carried out. After verifying the basic functions of our system, we attached a mobile phone at the input of the system and amplified our favorite songs.
Jetzt nehmen wir die Lautstärke.
Wie viel Strom geht durch?
Warte, jetzt kommt's.
Jetzt.
Leise.
Ist das maximal Lautstärke?
Nee.
Ich bin gerade mal 3 oder 4 Stufen höher.
Gut.
Ja, dann gib's doch.
Geht noch was.
Ja, mach.
Max.
Ja, genial.
Sehr stark.